In the summer of 1926, the German physicist Max Born published a paper analyzing a common physical process: two particles colliding. The paper contained a small footnote that was inspired by Einstein, angered both Heisenberg and Schrödinger, and at the same time revolutionized our understanding of fundamental physics. To truly grasp the meaning and significance of the Born rule, we turn to Einstein's contribution. Though Einstein is best known for his theory of relativity, it was his work on the photoelectric effect in 1905 that earned him the Nobel Prize. This honor was not bestowed on him immediately, however. In fact, Einstein's work was initially met with intense skepticism by most of the physics community, since it produced a seemingly obvious contradiction: that light was both a wave and a particle. What Einstein was trying to solve was a dilemma that arose from the results of an experiment by the German physicist Philipp Lenard. While investigating the behavior of light, Lenard found that shining a beam of light could affect the behavior of electrons in a metal. When the light was below a certain frequency, nothing seemed to happen, even if the intensity was increased. However, once the threshold frequency was reached, electrons were ejected from the metal. If he again increased the intensity of the light, this had no effect on the energy of the electrons. Further increasing the frequency of the light, however, resulted in ejected electrons with a higher energy. This posed a challenge because, according to Maxwell's theory of electromagnetic radiation, the energy of the electrons should depend on the intensity of light, not the frequency. By postulating that light comes in discrete packets of energy, or quanta, Einstein was able to explain this photoelectric effect. According to Einstein, the energy of these light quanta depended on their frequency multiplied by Planck's constant. So no matter how much you increase the intensity, you would just get more of the same discrete packets of energy being transferred to the electrons. It is only by increasing the frequency that you could cause the electrons to be ejected at higher energies. Though Einstein's theory fully explained Lenard's observations, the general physics community just could not accept that light might possibly be a particle. Max Planck said that Einstein missed the mark. Niels Bohr thought it had heuristic value, but did not give true insight into radiation. And even 11 years later, in 1916, Einstein wrote to a friend, "I do not doubt anymore the reality of radiation quanta, although I still stand quite alone in this conviction." Why did Einstein stand alone for so long? Well, put simply, there was already an extraordinary amount of evidence that light was a wave. Since the time of Newton, experimental observations had repeatedly confirmed that light underwent refraction, interference, and diffraction, phenomena that could only occur for waves. Moreover, Maxwell's theory explained all these observations within a framework that clearly described light as a wave. Physicists at the time just could not find a way to reconcile these facts with the idea that light was a particle. Even Niels Bohr himself was so convinced light particles were not real, he insisted that the apparent light quanta in his own atomic model must be somehow describable by waves. His ultimate goal was to remove the concept of light as a particle entirely from physics. While many physicists followed Bohr in having a strong distaste for this contradictory picture of light as both a wave and a particle, Einstein always maintained a more cautionary outlook. He simply acknowledged the apparent contradiction, but assumed it would be resolved once a deeper understanding was developed. The major step in this direction would occur in 1924 when Bohr teamed up with Hendrik Kramers and John Slater to formulate what came to be called BKS theory, a theory whose explicit goal was to get rid of Einstein's light quanta hypothesis. Ironically, though BKS wanted to get rid of Einstein's light quanta, its origins lie in another idea Einstein had himself. Throughout the early 1920s, in several of Einstein's letters with other physicists, he mentioned something called a ghost field, a field which could potentially reconcile the wave-particle contradiction of light. Though not fully worked out, the basic idea was that the ghost field was a field of light waves that guided the motion of light particles. Consequently, experiments that revealed the wave nature of light were capturing this ghost field, while experiments that revealed the particle nature of light were capturing Einstein's light quanta. Upon completing his PhD at Harvard in 1923, John Slater went to Europe to work as a researcher with Niels Bohr. He thought Einstein's idea was promising and wrote up a short paper outlining his own basic approach to it. The best way to understand Slater's theory is in relation to Bohr's model of the hydrogen atom. In Bohr's model, the atom consisted of the nucleus with an electron orbiting it. Crucially, the electron couldn't orbit at just any location, but could only orbit at certain fixed values. Values for which the angular momentum was equal to integer multiples of h bar, the reduced Planck's constant. Whenever the electron was in one of these orbits, the atom was considered to be in a stationary state. But at certain moments, the electron could transition between stationary states by either absorbing or emitting a photon, and the energy difference between the two orbits equaled the energy of the photon. Though Bohr's model accurately predicted the correct energy levels of the hydrogen atom and explained the observed hydrogen spectrum, it totally failed to account for the spectra of other atoms. With this failure, along with the fact that it made use of Einstein's light quanta, Bohr knew it needed to be drastically modified. It is in this context that Slater formulated his theory. According to him, when the atom is in one of Bohr's stationary states, it continuously emits a wave field. This wave field has no energy though, so it does not cause the atom to lose energy and spiral downward. It does, however, contain a set of frequencies that correspond exactly to the allowed transition frequencies between stationary states, and enables the wave field to guide the movement of light quanta. After publishing this paper, Slater then set out to work with Bohr on further developing the theory. They were joined by another researcher in Bohr's group. Like Bohr, Kramers did not like Einstein's light quanta hypothesis, likening it to medicine which cures a disease, but at the same time kills the patient. So it should come as no surprise that while Kramers and Bohr thought that Slater's idea held promise, there was one major objection they had with it. Slater was mistaken in thinking that light quanta really exist. Photons could not possibly be reconciled with the phenomenon of interference. Moreover, the fact that these discrete packets of light quanta had energies equal to hf entirely depended on the wave picture to determine the frequency. So it was inherently filled with contradiction. The photon had to be removed from the theory. So while Slater's initial idea was to provide a synthesis of the wave picture of light with the particle picture, in the newly developed BKS theory, the photon was entirely gone. And instead, the focus shifted to the transitions that the electron underwent inside the atom. Transitions known as quantum jumps. Jumps that Bohr clearly knew were physical and real, regardless of the reality of photons. Though this shift seems subtle, it proved to be incredibly important in the steps taken toward the development of quantum theory. Under the BKS framework, Slater's field no longer unified the wave picture of light with the particle picture. Instead, it now conceptually harmonized the wave picture of light with the physical process of quantum jumps. As one of the founders of quantum mechanics, Werner Heisenberg would describe it, the first and very interesting step toward a real understanding of quantum theory was taken by Bohr, Kramers, and Slater in 1924. The electromagnetic waves were interpreted not as real waves, but as probability waves. An interesting consequence of this idea was that both energy and momentum were not conserved in every single event. According to BKS theory, the two famous conservation laws were true only as a statistical average, which made BKS testable by experiment almost immediately. The next year, two German experimental physicists, Walter Botha and Hans Geiger, devised an experiment that would test the predictions of BKS. They began with a beam of light in the form of X-rays aimed at a target material. Through a process known as Compton scattering, if the light hit an electron, then the electron would go scattering in one direction and a photon would scatter in the opposite direction. By detecting these two events and comparing the timing, the conservation of energy and momentum could be tested. The results were realized quickly. Geiger and Botha found that these laws did indeed hold for every event, and were not just a statistical average as BKS predicted. So BKS was wrong. However, it did contain an essential feature of the quantum theory soon to be discovered, namely the probability wave. A concept that would be taken up by Max Born and formulated in a mathematically precise way by him just a few years later. But before the Born rule could be discovered, there were two important steps that needed to occur: the development of matrix mechanics and wave mechanics, the first two mathematically consistent formulations of quantum mechanics. I made an entire video going into the details of each of these, and I've linked them both below. So if you want to learn more about how they were discovered, go check those out after this. For now, all you need is a short summary that will put Born's discovery in the proper context. In May 1925, Werner Heisenberg was working as a researcher under the mentorship of Max Born. Because of a severe attack of hay fever, Heisenberg requested to go on a retreat for 14 days to a nearby island called Heligoland. It was on this trip that Heisenberg discovered the essential seed of quantum mechanics. While pondering over the inadequacies of Bohr's model of the atom, he made a brilliant conceptual leap. He realized that experimentalists never actually observe the orbits of the electron, but only observe spectra, which are the effects of the quantum jumps. So Heisenberg removed every reference to unobservable quantities in his theory, and found a way to describe the electron's position and momentum purely in terms of observable quantities like the frequencies and intensities found in atomic spectra. By doing this, he also discovered that momentum and position obeyed surprising multiplication rules when written in this way. The order in which you wrote them mattered. He had no clue what this was, but after returning from his trip, he showed his work to Born, who eventually realized that it was matrix multiplication, a mathematical concept that was entirely unheard of to most physicists at the time. Together, Heisenberg and Born then worked with Pascual Jordan to further develop this theory, and just 60 days later, published a paper with a fully worked out version of quantum mechanics, based entirely on matrices, what came to be known as matrix mechanics. The next step towards Born's rule occurred just 1 year later when Schrödinger discovered wave mechanics, an alternative formulation of quantum theory based on his now famous wave equation. This new theory was developed over a series of 6 remarkable papers that Schrödinger published in the year 1926. At this point, most physicists had accepted that light was in some way both a wave and a particle. Moreover, Louis de Broglie had shown that matter had also exhibited this wave-particle duality. However, Schrödinger remained one of the few that refused to accept the particle nature of light. In his third paper on wave mechanics, he argued that waves were the ultimate reality, and that particles were just derivatives of waves, or localized wave packets. He showed that waves can indeed form a stable wave packet for the simple case of one dimension, and concluded the paper by saying, "We can definitely foresee that in a similar way, wave groups are the representation by wave mechanics of the hydrogen atom, but the technical difficulties are greater." Not only was Schrödinger skeptical of photons, but he also was unwilling to accept the idea of Bohr's quantum jumps in the atom. For Schrödinger, these ideas were just too divorced from a classical and visualizable picture that he thought physics was meant to provide. His great hope was that wave mechanics would be able to explain the apparent wave-particle duality of light and matter by providing a true picture where the most fundamental physical objects were waves obeying the Schrödinger equation. As for the quantum jumps, let's just say Schrödinger hoped to get rid of those too. Amazingly, Schrödinger's wave mechanics and Heisenberg's matrix mechanics were both able to explain the observed spectrum of the hydrogen atom. And it was not long before Schrödinger showed that both versions of quantum mechanics were equivalent. yet still they had drastically different frameworks. To most physicists, Heisenberg's matrix mechanics provided the right conceptual framework by removing electron orbits and strictly adhering to the reality of only observable quantities. The Schrödinger equation, on the other hand, provided the most convenient way to make calculations, yet it was totally unclear how to actually interpret what the wave function represented. For the hydrogen atom, Schrödinger interpreted the electron as a wave literally distributed over space, and described by his wave function. It was visualizable in this case, but as soon as you considered more electrons, it was clear that the wave function could not possibly exist in physical space. One of the most prominent physicists at the time described the situation succinctly. It is this dilemma that Max Born provided a definitive solution to. His great insight was to remove the physical interpretation of Schrödinger, but hold on to the mathematical framework of wave mechanics. In the summer of 1926, Born published a paper where he analyzed the collision of two particles. He chose to do this using Schrödinger's wave mechanics. It was the first time this problem had ever been analyzed in either quantum mechanical framework. To be more precise, he considered a steady beam of particles moving in the z direction, given by this function. This was meant to model electrons interacting with a stable atom. Now, the incoming electrons have an initial momenta, which is altered by the interaction. So the end result is that they should scatter at various angles. Using this as his starting point, he then used an approximation technique known as perturbation theory and found that the deflected wave must have the following form. Now, it looks incredibly complicated, but the main thing to take away from this is that when you get far enough away from the interaction, you just have electrons moving freely, which is exactly what we had before the interaction, except now the electrons have different momenta. So the end result is just a bunch of different initial functions added together. The technical term is that the outcome is a superposition of initial solutions. From here, Born suddenly realized that there was only one meaning that this first term phi could possibly have in this context. If performed as an actual experiment, the only thing that would be observed would be the angle at which electrons collided with a detector. And since all of these states won't be observed all at once, they must simply be the possible final states after the collision, meaning phi must be some sort of weight factor for each state. Or in the context of an experiment, the probability of detecting the electron at a given angle. In the actual paper, Born initially stated that phi gave the probability, but then later added a footnote correcting himself, saying that the probability was proportional to phi squared. In a later paper, Born then made his interpretation even more explicit and wrote the Born rule as we recognize it today. Born went even further and said that Schrödinger's quantum mechanics then gives a completely definite answer to the question of the effect of a collision. However, one is not dealing with any causal relationship. One gets no answer to the question, what is the state after the collision, but only to the question, how probable is a prescribed effect of the collision. This raises the whole problem of determinism. The weirdness of quantum mechanics and all the thorny philosophical issues inherent in this statement from Born have remained with the physics community ever since. Born initially gave Einstein full credit for inspiring this probabilistic interpretation of the wave function, thanks to his earlier ghost field idea. It is in response to the initial collision paper and a letter that Born wrote him that Einstein made his famous claim that God does not play dice. Not only was Einstein not happy with it, but Heisenberg and Schrödinger were both initially angered as well. Heisenberg because Born used wave mechanics to solve what remained an open problem in matrix mechanics, and Schrödinger because Born had found a way to reinterpret his wave mechanics in a way consistent with Heisenberg's philosophy. Soon after Born's work, it became clear to most physicists that there was no other way to interpret the wave function. Particles were real. but they were governed by laws of probability. The probability itself, however, propagated deterministically according to Schrödinger's equation. Born's rule quickly became the pivotal concept connecting theory to experiment, and found a central place in the quantum framework. This place would be permanently established when the subsequent work of two famous physicists succeeded in placing quantum theory on a rigorous axiomatic foundation. Eventually, in 1954, the Nobel Prize was awarded to Max Born for his discovery. It was also awarded to the experimentalist Walter Botha, who paved the way for Born by showing that BKS theory was incorrect. Geiger certainly deserved a share as well, but sadly passed away in 1945, so was not given the prize. As von Neumann would describe the significance of Born's work, the Born rule became the only consistent way to interpret quantum mechanics. On a similar note, I've learned that the only consistent way to get better at math and science is hard work and tons of practice problems. I love Brilliant because it helps you improve at problem solving right away for free. Lately, I've enjoyed going through their new course on algorithms, which has encouraged me to think more deeply about how best to structure the code I write. Not just this course, but every course on Brilliant is filled with visual, interactive lessons and practice problems that are personalized just for you. The whole curriculum is designed by world-class teachers for anyone between the ages of 10 and 110. So whatever stage you're at, Brilliant can help you actively learn and excel at math, science, and coding. To start learning for free for a full 30 days, go to brilliant.org/abidebyreason. Scan the QR code on screen or click on the link in the description. Brilliant's also given my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Thank you to Brilliant for sponsoring this video, and thank you for watching.